Thank you, Wim and Han. So what we noticed in the previous presentation that, of course, the costs are a very important part of the decision, of any decision, I guess. And the difference in cost between aluminium and copper is quite high. However, if we look at the cables and we include all the costs over a lifetime, then this picture could be different. So if you want to do and make an investment decision, we should consider all the costs. So that's why we did a life cycle cost analysis. So I'll tell you first a little bit about the life cycle cost analysis. Then I'll discuss the CAPEX and OPEX involved in a cable. We build a model, which I'll explain. We'll discuss the cables that we compared for this analysis. Then we used the methodology of a net present value, which I will briefly explain. We've used some parameters for that. Then we have the results and the conclusions. Yeah, so when people do an investment, of course you look at the initial investment costs, but there's also, after the investment, there's some operational costs. This is what we call the OPEX. So the initial investment will be CAPEX, capital expenditures, and then the OPEX is operational expenditures. What we notice now is that investments are highly based on the initial investment only. However, if you want to compare costs, you should consider the lifetime cost to get a better understanding of all the costs of an asset. And that's what we did, this analysis, to get a better picture of this, of two comparable cables. So if you do the life cycle cost analysis, you can find the economical optimal decision. We build a computational model which can compare several cables, and then we've chosen a couple of cables that we want to compare. And these values are discounted to the net present value. So as I already said, there's CAPEX and OPEX involved. So the CAPEX is the initial investment. In the case of cables, this is the equipment cost, so that will be the cable, meaning conductor, but also the insulation material and such. And the installation cost, of course. You want to put the cable under the ground. After the installation, you have operational costs, which is the O&M cost, operational maintenance cost, but also electrical losses. And in the end, there's a residual value that could be taken if you take the cable out of the ground. For this analysis, we used mainly the DNVGL cost database. We built a database that has cost information from the industry, which we check and update regularly. So this makes it possible for us to make an estimation of cost, of labor cost, but also equipment cost and construction cost and such. And we were able to get some failure data from a European network operator, which also consisted the conductor type, so the difference between copper and aluminum. And then we could see if there's a difference between that. However, this data was only from several years, so it wasn't enough to get some harsh conclusions out of it. But we hope that more and more data will come, and people will keep data, failure data of between aluminum and copper conductors. So the cables that we want to compare, if you want to compare a copper or aluminum cable, the cross section should be different because, as Wim said, the conductivity is different. For copper is a better conductive material than aluminum. So what we usually do is, if we have a 400 square millimeter cross section for copper, you compare it with 630 for aluminum, and 1,600, and then 1,200 and 2,000. This gives similar losses, not exactly the same, but it has similar losses, and this is a way to compare cables. So we've used several voltage levels for this analysis. So we've used 20 kV, 110 kV, and 400 kV. And then within these voltage levels, we've used cables of different cross sections, as seen in the table, which are the before mentioned cross section. So we have 3 voltage levels that are compared, 3 cross sections per conductor, and then we've used this market data from manufacturer to estimate the cost. So now I'll go through all the costs involved. Of course, it highly depends on several choices, but also for installation, for instance, we focused on the Netherlands. But yeah, some important parameters are soil type, trench depth, width, and cover. And if there are many obstacles, the urbanization degree is important. If it's direct buried or if you lay it in ducts. The permits are important, and labor costs. As you see, this is highly dependent on the region and the country. So we had to make we made some choices for this, but we took normal circumstances within the Netherlands, which is direct buried in the Netherlands in an urban environment, and we have included 70% paving cost. The operation and maintenance cost. This highly depends on the strategy of the system operator. Even within the Netherlands, there's different strategies with the system between the system operators. And if you look international, this is also different. And also what we've noticed is that the system operators do not make a distinction between the conductor type. So for aluminum, but also for copper cables, they use the same strategy, which makes that in their maintenance, there's no difference in cost. However, if there's failures, which is of course a significant part of the O&M, we think that there could be a difference between the conductor types, so between copper and aluminum, in failure amounts of failures. However, like I said before, we've analyzed some failure statistics, but the amount of data is very limited, and we're hoping that from now on more data, failure statistic data with the conductor type will be kept so that we can do some more research in the future about it. So now we were not able to take hard conclusions out of it. So like I said, the losses are comparable between the chosen cross sections, but there's still a small difference in conductivity, which has been considered. And in order to calculate the losses, of course, the length and the load capacity is important, cross section, and then the conductor material, the voltage level, and like if the cross sections, especially if they become bigger, then the skin effect takes place. So the small difference in electrical losses has been considered over the lifetime of these cables. And then there's a residual value. So we know that the value of copper is higher than the value of aluminum, and this might change in the future as well. We cannot make an estimate of the value of copper in 40 or 50 years, or aluminum. But we think that the copper value will increase. However, since currently the cables are left in the ground many times because construction costs are quite high, but also the municipalities don't like it if, of course, you open the streets too often. So now the system operators leave the cables in the ground most of the time. So we've decided not to include the residual value. So they've been excluded from this analysis now. So we've built a model. This calculates the cost for the different parameters. Then it calculates the net present value of these costs. It sums it up over the lifetime. And then we can compare the copper and aluminum cables. So we made this model in Excel, and we can change the type of cables, and so we've chosen a couple of them. Yeah, now I'll briefly discuss the net present value. Yeah, the net present value is used to measure the value of future cash flows. Since the future cash flow has a different value than current cash flow. Then in order to get a sense of the difference in this value, the net present value methodology is used. It's also commonly used to determine if projects are worth investing in or to compare several projects with each other. Since we consider only costs in this analysis, so the benefits are equal for the same cables. And the cable with the lowest net present value can be considered the better economically investment in this case. So what we included in the lifetime cost are the cable cost, the installation cost, the losses, and the O&M cost. And we've only considered the losses once, but they're on this slide 2 times. The net present value, so to come back to that, the net present value, this is the equation. As you see, the CT are the initial costs. CT are the net cash flows in the future. So these are would usually be benefits minus costs, but here it's only costs in the future. You divide this by 1 plus R, T should be a 1, over time, and then you can calculate the future cash flows in the current situation, so in this year. And then we also have the initial cost, so we add those together to get the net present value of the total cost of the lifetime of this cable. Within the model, also for the equation we saw before, we've chosen some parameters. And the interest rate is 3%. The area is urban, and the electricity price is €50 per megawatt hour. Lifetime, we've chosen 50 years of cable, although sometimes system operators use it even longer. It's a 3-phase cable, and we've used 1 kilometer of length just to compare the cables. So now we come to the results of the chosen cables. As you see in the graph, the difference is not very high. You also see a decrease in the difference when the cross sections increase. And overall, you see a 3% difference in cost between the conductors over the entire lifetime, which is a very low percentage if you compare it to the initial difference between copper and aluminum cost, just per weight or per kilogram. And I also want to show the next graphs. What you see here is that the insulation and material costs are 60 to 65%, which is only a part of the total cost of a cable in the lifetime. We did not include the residual value here. But yeah, you see that if you only look at the initial investment cost, you take only part of the total cost of an asset. And especially for cables, this is still a significant amount. So we've got some conclusions. So the large investment cost difference between the cable has been reduced to about 3% if you look over the total lifetime cost of the cable. So this is a large decrease. And the conductor price difference between copper and aluminum is high, but looking at the lifetime cost, this difference is almost negligible. We think that investment decisions should be based on the total lifetime cost, since this gives a better understanding of all the costs involved, instead of just looking at the initial investment. And in order to get a better understanding of the difference in operational costs, since we couldn't get a draw clear conclusions from the failure statistics that we had, we hope that more failure statistics with conductor types will be kept so that we can do a better analysis in the future. And currently we're doing a sensitivity analysis to see how the parameters influence the outcome of the model. Of course, this will give us a better insight of all the costs and how the model, or like what what has the biggest influence on the outcome. So now we want to have some final conclusions of the part 1 and part 2 together. As we heard from the first part, copper has better electrical, mechanical, and chemical properties in aluminum. We use as a conducting material in cables. What we found is that the preference for aluminum is based on the lower initial cost, CAPEX. However, looking at the total life cycle, the difference in cost appears to be negligible, so including the OPEX. Aluminum is far more than copper involved in the degradation process. It is recommendable to indicate the conductor material in failure statistics. And in failure investigation, more attention should be paid to the impact of conducting material. So far, the focus has only been on the insulation material, but we think that also the conducting material will have an influence. So now we've come to the end of this presentation already. Thank you for your attention, and if there are questions, you can ask them now.